My name is Dr. KCH Apparao, working as an associate professor in a mechanical engineering department. Today, I would like to explain about definition terminology of heat conduction equations. Heat conduction in Cartesian coordinate system, heat conduction in spherical coordinate system, and cylindrical coordinate system. What is steady state conditions? We'll see different definitions and terminologies which are related to heat conductions. Okay, so first of all, we'll see what is steady state process or steady state condition. Steady state condition means the temperature does not change with respect to time, dt. It means dt by d small t is equal to 0. So temperature does not change with respect to time. So that is steady state condition. So we'll see. So a steady process is one which is not depend upon time. So that is the rate of heat transfer does not change or does not vary with time. We'll see. So dt by d small t is equal to 0. The opposite one is the unsteady state condition, that is temperature change with respect to time. We'll see later that one also. So this is the condition. Every system starts with unsteady state condition, then it reaches to steady state condition. Now we'll see the dimensional heat conduction equations. One dimensional heat conduction. What is one dimensional heat conduction equation? Suppose heat conduction, either conduction of heat either in any direction, either it is x direction or y direction or z direction. If the heat conduction of heat passes in a one direction, either suppose it is in x direction, so that is called one dimensional heat conduction equation. We know that Laplace equation, dou square t by dou x square plus dou square t by d square t by dy square plus d square t by dz square. So this shows the heat conduction in three directions: in x direction and y direction, z direction. If you consider only d square t by dx square, then this is the one dimensional heat conduction equation. Just we are neglecting different directions, so we are taking only one direction. If you consider d square t by dy square is equal to 0, otherwise d square t by dz square is equal to 0. This here we are choosing only, we are considering only one direction, either x direction or y direction or z direction. So this is called one dimensional heat conduction equation. We'll see what is the definition of this one here. If the temperature varies only in x direction, either in x direction, y direction, any direction, considering only one direction. So if you consider it is in x direction, then Laplacian operators takes the only one form, that is called d square t by dx square. It is called, so that one is called one dimensional heat conduction equation. Okay, by using this one we can find out the conduction equation also. Conduction equation for the slabs, conduction equation for the cylinders and spheres also. Now we will see. Write three-dimensional heat conduction equation in Cartesian coordinate system. So we know all the already derived formula. Suppose this is the three dimensional. This one is the x, y, and z. Just we are considering only one rectangular piece or symbol. Okay. So this is the x. Thickness of the element is equal to dx. So x center is, this one is the x dx leaving. Similarly, this one is the y. So this surface is equal to dy. So dy is the thickness. This is the thickness of the, this is the dy. Similarly, this one is the dz. So this is the Cartesian coordinate system. We know the final derived formula based upon the net heat conducted into the element and heat generated into the element is equal to increased heat energy in the element and work done by the element. So you know that formula. So this is the formula. Three-dimensional formula is equal to net heat conducted into the element. Element is equal to dx dy dz element. Okay. Per unit volume plus internal heat generated heat. So small q into volume. Okay. Next, increase in internal energy. Increase in internal means rho Cp into volume dx, dy, dz. So these are the values. Here we have to calculate the net heat conducted into the element dx, dy, dz. So net heat conducted into element, that is the formula. We already derived this one with respect to so x direction, that is the kx into d square t by dx square plus in y direction ky into d square t by d y square plus kz into d square t by dz square, okay, into volume dx dy dz plus internal heat generated, internal energy or increased, no, that one is the internal heat generated per unit volume. So the value is equal to small q heat flux into volume dx dy and dz is equal to, you know that rho Cp, increase in internal energy, rho Cp into uh, volume dx dy and dz. So in three areas, volume will be cancelled. The final formula, if you consider the k, the common letter. So suppose if you consider this is the homogeneous body, then kx is equal to ky is equal to kz. The final formula will be like this one. You can see the formula for the heat conduction equation in Cartesian coordinate system. So that is the d square t by dx square plus d square t by dy square plus d square t by dz square plus q by k is equal to rho Cp by k into dt. Okay, so that is the formula you can see here. So kx into dou square t by dou x square, ky into dou square t by dou y square, into kz into dou square t by dou y square into q, the heat flux, rho Cp into dou t by dou small t. This was the, if it is in steady state, it will be 0. Then the formula will be like this one, d square t by dx square plus d square t by dy square plus d square t by dz square plus q by k. We are taking k as the common, and rho Cp by k into dt by d small t. This is the final formula for the heat conduction equation in Cartesian coordinate system. Okay, so rho Cp by K or K by rho Cp. So this is called alpha. Alpha, it is the thermal diffusivity. We'll see what is thermal diffusivity in next slide. We'll see what is the importance of the thermal diffusivity. So K by rho Cp is the thermal diffusivity. You can rewrite like this one, 1 by alpha into dt by d small d. So this is the final formula for the uh, heat conduction equation in Cartesian coordinate system. Okay. Similarly, we can find out the heat conduction equation in cylindrical coordinate system, in this spherical coordinate system also we'll see. So just I am writing here what is the formulas of the heat conduction equation in cylindrical coordinate system and spherical coordinate system. So based upon this first formula, which is heat conduction equation in Cartesian coordinate system, by using this one we can derive the remaining equations also. Okay, so this is the final formula. You can consider this one. Okay. Next, so write three-dimensional heat conduction equation in a cylindrical coordinate system. Cylindrical coordinate system. Cylindrical means first of all we will take this small cylindrical piece, then we will derive this one heat conduction in that cylindrical uh, particle cylindrical piece. Then we just find the heat conduction equation. Similarly, what was explained in the previous that one, heat conduction equation in Cartesian coordinate system. Okay, just here also this is the x, y and z. Just your x and y, you are taking some angle. This is the angle pi. This is the d pi. Okay, so from here just we are taking small elemental area. Okay. So this is the distance is equal to radius r, the thickness is equal to dr. So this is the elemental area of cylindrical coordinate system. Here we will see the parameter in case of x and y. So x is equal to r cos theta cos pi, y is equal to r sin pi. So these are the parameters. In case of in the first equation, you know that dou square t by dou x square plus dou square t by dou y square plus d square t by dz square plus q by k is equal to 1 by alpha into d capital T by d small d. This is the formula here. So the vertical axis here z is common, but x and y components will be changed in the form of radius r and angle pi. So here this portion will be changed. Okay, so that portion is like this one, dou square t by dou r square or d square t by dr square. The formula here you can see or we can observe this one. In the place of x, we see this one. It means so d square t by dr square plus 1 by r into dt by dr, 1 by r square into dt by dq d pi square. Here just we can observe the formula here. So it means x and y components will be changed. In the place of this one, we will get this one. D square, dou square t by dou r square plus 1 by r into dou t by dou r plus 1 by r square into, okay, 1 by r square into dou square t by dou pi square. Okay. So in place of x and y, X component, Y components will be changed in the thus with respect to R cos phi and R sin phi. Okay, so this way. So this is the final formula. Only two parameters will be changed for the with compared to Cartesian coordinate system in with respect to cylindrical coordinate system. Okay, so these terms you have to remember this one. So this is the formula for the heat conduction in cylindrical coordinate system. Similarly, we'll see the heat conduction in spherical coordinate system also. This is the formula. You can remember this one to find out the spherical coordinate system or heat conduction in the spherical coordinate system. Those were T by r square, r square into sin square theta and d pi square and dou by r square sin theta d theta sin theta dou t by dou theta. So this is the formula you can find out. Here three parameters including z also will be changed because that is in spherical coordinate system. Okay. Now we'll see the thermal diffusivity. So in the previous slide I already told that one thermal diffusivity, that is the d square t by dx square plus d square t by dy square plus d square t by dz square plus q by k is equal to 1 by alpha into dt by d small. So this is the heat conduction in Cartesian coordinate system. So here 1 by alpha, 1 by alpha means rho cp by k. So this is called thermal diffusivity. So we'll see what is thermal diffusivity, what is the importance of this one. Uh, Thermal diffusivity, the physical significance of the thermal diffusivity is that it tells us how fast heat is propagated or it diffuses through a material during changes of the temperature with respect to time. Okay. So when the temperature is changing, so how fast heat is propagated in that material. So that is called thermal diffusivity. The larger the thermal diffusivity, the shortest is the time required for the upward of heat to percent vapor into solid. I will explain clearly. Here you can see this one. What is the mean of what is the importance of the thermal diffusivity? Thermal diffusivity, it is a material property. Okay, it represents how fast thermal energy diffuses or passes through a material. How fast thermal energy diffuses through the particular material. So that is called thermal diffusivity. Okay, that is the alpha is equal to K by thermal conductivity by rho into Cp, density into specific heat. That is called. The formula for the thermal diffusivity is equal to, this alpha is equal to K by rho Cp. K is the thermal conductivity, heat conducted by rho Cp, that shows the heat stored, heat conducted by heat stored. The units of thermal conductivity are meter square per second. Okay. So heat storage capacity of the material, that is the specific heat per unit mass in case of mass, rho Cp in case of volume, rho Cp per unit volume. Okay. So you have to consider for the solving of material properties like thermal diffusivity. Here we can observe different types of thermal diffusivity. Silver has the highest thermal diffusivity, 149 into 10 to the power minus 6 meters square per second. Next, gold, copper, and aluminium, very near. Next, iron, mercury. Okay. So this is the material property to diffuse heat through that material. Okay. Next one is the specific heat. what is meant by specific heat? We already saw this one in that thermal diffusivity alpha is equal to rho Cp by K, K by rho Cp. Okay, thermal conductivity, stored energy with respect to volume. Cp is the specific heat. Okay, so what is specific heat? We'll see. What is the definition of the specific heat? Specific heat is the energy required to raise the temperature of a unit mass of a substance by 1 degree. Energy required to raise the temperature of unit mass of a substance by 1 degree. Okay. So this is called specific heat. So to raise the temperature, 1 degree temperature, so what amount of energy is required? That shows the specific heat. Right? Different materials store heat differently. The storing of heat is depend upon the type of the material. The property specific heat indicates the measure of a material's ability to store the thermal conductivity. Okay. Specific heat of water is the 4.18 kilojoule per kg Kelvin. Specific heat of the iron, so it is the 0.45. It means specific heat of the water is the 4 times greater than the specific heat of the iron. It means water, it, it, uh, it can store, it has the ability to store the heat energy compared to iron. So water can store the almost 10 times the energy that stored in the iron. Okay. So this is the one of the material property similar to thermal diffusivity. Okay. So how to remember this one? So next one we'll see thermal conductivity. I think, okay. It is the material property. It varies with respect to uh, different materials. So some material have high thermal conductivity, some material have low thermal conductivity. Mainly solids, metals have high thermal conductivity because conductivity uh, occurs only in solids, solid material. So what is thermal conductivity is represented by K. I think it was explained in last class also. It is the measure of ability of a material to conduct heat. Cp is the ability of material to store the heat energy. It is the ability of material to conduct heat. Conduct heat. So thermal conductivity of water very less, but the thermal conductivity iron is very high. For fluids, conductivity is very less. Okay, conduction only occurs in mainly occurs in the solids because conduction occurs due to the uh, lattice vibration, particle vibration, or movement of the electrons, not by movement of the particles. Okay, so in fluids, particles are very loosely packed. They can move from one place to another place. Okay, so because of that one, thermal conductivity is very good in solids compared to fluids. Here we will see thermal conductivity of the water is equal to 0.608 kilojoule per kg Kelvin, but thermal conductivity of the iron very high, thermal conductivity of the aluminum very high, copper is very high, silver is very high. Okay. Iron can conduct heat more than 100 times faster than the water. In case of Cp, specific heat, water has highest more specific heat compared to iron. But in case of thermal conductivity, okay, iron has 100 times faster than the water. Okay, you can observe this one. Thermal conductivity K, it is represented by K. Thermal conductivity is defined as the rate of heat transfer through a unit thickness of material per unit area per unit temperature difference. Okay. Unit thickness of material per unit area per unit temperature difference. So that is called thermal conductivity. It depends on physical structure of material, because in solids the structure is different. In fluid structures they don't have any structure. Okay. So based upon the structures, thermal diffusion, thermal conductivity will be varied. Next, it also depends upon the atoms and molecules, because in solids, atoms are closely packed, but in fluids, atoms are loosely packed. Okay, they can move from one place to another place. Okay, which depends on the state of matter also, state of the matter. So these are the parameters on which thermal conductivity will depends. Okay. Now we'll see what is meant by boundary conditions. Okay. So initial conditions and boundary conditions. So these boundary conditions are very important to define the heat transfer rate. Hmm. Okay. The set equations derived so far describe the whole class of conduction phenomena in the most general form. You know this one already discussed this one. The temperature distribution in a medium of given form and size can be solving by an appropriate equations. Okay. So solving of temperature distribution, it means solving of the Q value, rate of heat, or heat flux value, small q, is solved by, is determined by the help of the boundary conditions. Okay. So deriving the rate of heat transfer in any uh, slab or cylinder or spherical bodies also, boundary conditions are very important. Okay. Suppose if you take this one slab, here boundary condition is x is equal to 0, this is x is equal to L, temperature is equal to T1, temperature is equal to T2. So this type of boundary conditions are very important to find the uh, to solve the, or to find the rate of heat transfer Q value, like this one. We'll see more details regarding the boundary conditions here. So initial and boundary conditions, they need. So general differential equations, these equations describe the generalized phenomena. So dou square T by dou x square is equal to 0. If you solve this one, you will get this formula T is equal to C1x plus C2. Okay. To solve this one, you have to take some boundary conditions. Okay. So by using the boundary conditions, you have to find out the C1 and C2 constants. Then you will get the final formula. Okay. Temperature equation. Okay. So here temperature is equal to 60 degrees, x is equal to 0, and t is equal to it means these are the boundary conditions. Suppose at x is equal to 0, temperature is equal to 60. At x is equal to 5, temperature is equal to 25. So these are the boundary conditions, initial boundary conditions, uh, two boundary, so starting and final boundary conditions. Based upon these boundary conditions, we can solve this equation. Minus 7x plus 60, that is a temperature equation. Okay. So boundary conditions are very important for finding the rate of heat transfer in any object, either it is in cylindrical form, spherical form, or in slab also, rectangular form. Okay. So initial and boundary conditions provides unique solution. Here, how many initial conditions and boundary conditions we need for completely defining the problem? Okay. The number of initial conditions and boundary conditions, the direction of each independent variable of a problem is equal to the order of highest derivative. So it is the order of highest derivative means dt by dx. One type, d square t by dx square. Another type, d cube. So it means, so second order, first order, based upon the order, boundary conditions will depend upon this one. Here we'll see some examples of this one. So this is the initial boundary condition, initial conditions and boundary conditions. Initial boundary x is equal to 0. This one is the temperature is equal to 60. X is equal to 5. Temperature is equal to 25. By using this boundary condition, you can find out the rate of heat transfer in this condition. Okay. Here, just like this is the formula, you know this one. This is the here dt by d small d. Okay. Here initial condition is equal to 1. Suppose d square t by dx square. Boundary conditions here 2. D square t by dy square. So this is 2. Second order. So boundary conditions are 2. Okay. Here also boundary conditions 2. Here also boundary conditions 2. So based upon the order of the highest derivative of GDU, general differential equation. Order of highest derivative here 1, here 2. So based upon this one, we will choose the boundary condition. So this is just small information regarding the boundary condition. Next, we'll see finally just like importance of heat transfer, and we'll see here also difference between the thermodynamics and the heat transfer. Just conclusive point. Thermodynamics tells only how much heat is transferred, del Q, how much work is done, del W. Here, next to final state of the system. These are the main important points. But in heat transfer, we'll see heat transfer rate. It means how within the modes, how dq temperature difference is transferred by what type of modes, either conduction, convection, radiation. Rate of heat transfer q or heat flux small q. Okay. At what rate? At what rate means small q. You can find out temperature distribution inside the body, only in the body. So rate of heat transfer or heat flux. You can focus on heat transfer only focus on the q or small q, but thermodynamics focus on work done also. Final state of the system also. Here only heat transfer rate or heat flux only. Okay. No need of explaining about the energy. Okay. Here only heat transfer rates. Next, we will see some applications of heat transfer. What is the importance of application? So, heat transfer is a very important subject. It is associated with many areas, engineering in different branches also, and biological system also. We have to study about the uh, heat transfer, because in our body condition, based upon the climatic condition, the temperature is system is changing. So sometimes temperature will be taken by body. Sometimes body will lose the temperatures based upon the climatic conditions. So we have to study about that in that area also. Next, first energy production and conversion. Energy production of the energy or preparation of either heat energy or any current. or power generation. So we'll see steam power plants. Here also, so heat transfer is very important phenomena for the developing of the steam power plant. Next, solar energy conversion. Here also, by radiation, it comes by the phenomena, by the mode of radiation, heat transfer takes place, or heat energy is converted into solar system, solar energy. No, sorry, solar energy or heat energy is converted into electrical energy. So here also the importance of heat transfer, subject to need of application of heat transfer is very uh, needed. Refrigerating system, air conditioning system also. Next to domestic applications in ovens, we'll see also in that case uh, radiation heat transfer, stoves, just like heat conduction, toasting of any objects. Here also heat transfer. So need of heat transfer is very huge in many areas. Next to cooling of electronic equipments, just like we'll see some pins on generators and air compressors and transformers also for the cooling purposes. Just motor like automobile sector for the cooling of engines, we'll use that some pins, rectangular or circle types of pins we'll use for only for the just cooling purpose of the engine. So in many areas you will see the application of heat transfer in manufacturing and materials processing also, welding, casting, soldering, laser machining, in automobile, radiator, aircraft designs, in so many areas the applications of heat transfer we can observe. So this is the uh, small definition terminology regarding this heat conduction processes. Okay, so these are the different books to refer these topics. Thank you for the listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.